Então. So good evening, everyone. Good evening. My name is Gabriela, and we will be talking today about probabilistic machine learning. So the lecture is divided in two parts. Basically, we will start with talking purely about probabilistic machine learning, what it is, some concepts that I deem important to the field, and then we are going to talk about particularly about the results from my master's thesis that I did at KTH on this topic. So, exactly. So, everything started at KTH. So I did my thesis there, and I did my master's program on machine learning. And at the end, at the end of the program, I did my thesis at ABB in the Corporate Research Center. And so this was basically last year. And now I am working as a machine learning research engineer at Luclet. So this is the little bit about my path in Sweden, since I moved to Sweden. So, some few words before we start. I will hopefully reserve some minutes at the end for questions. But I would really like you to interrupt whenever you feel like there is a weird concept or there is something that is not clear for you. So let's keep it interactive and just interrupt me whenever you need it. Yes, so this is a possible definition of machine learning. Machine learning is the science of learning from data. So learning means that we need some sort of framework to define what learning really is. So during this talk, we are going to understand learning as inferring plausible models to explain data that you observe. So that's our definition. And an important part of it is by taking into account uncertainty in different levels of reasoning. So we are going to keep this word with us from the beginning to the end. And yes, right now it should sound quite abstract. So let's go directly to an illustrative example. This is really an illustrative example. Let's imagine that we have some data connecting the temperature in the city of Stockholm and the number of people who take the bike in the city. So we have some points. Basically, every point here represents a day, for instance. And we have this data. So a common task for a machine learning practitioner is what? We have some data, and we want to extract some knowledge from it. We want to understand something from this data. We want to do some sort of tasks, such as a prediction, forecasting, something. So where is the uncertainty here, then? We can understand, just from this simple example, already many different sources of uncertainty. One of them, in the lowest level, would be... Can you hear me properly? Yes? Cool. So one of them will be, in the lowest level, uncertainty in our measurements. Can I trust that really this number of people taking the bike in Stockholm is correct? Probably this is an estimate, so probably there is some noise over there. We already start off with some sort of uncertainty. All right? So, oh yeah, I just put this in question mark here to say we would like to predict something, such as what is the number of people biking that in a particular day, given a certain temperature. This is an example of a task that we would like to perform. All right. So basically, one of the things that we could do is to find a linear relationship between these two variables by estimating some parameters, basically the intercept and the slope of this line. Yes, but let's go back to our uncertainty. So this is our first source of uncertainty in our measurements. So from there, we have one source of uncertainty. Another possible source is our parameters. Given that this is a linear system, a linear model, we have these two parameters, that's theta 0, theta 1, but we don't really know what are the optimal values of these parameters for us to predict something, for us to do our task. So this is another source of uncertainty. And at the highest level, we're not even sure if a linear relationship between these two variables would be the most appropriate one. Would a neural network be more appropriate? And if so, how many layers would we use? So this is the sort of uncertainty connected to the structure of the model that is the highest level of uncertainty. Cool. So uncertainty is something that is central to many problems. So here I will mention some of them, such as forecasting, decision making. We want to be sure when we take a decision how much we can rely on that decision, as well as in situations when we have limited, noisy, or missing incomplete data. I put this one here in bold because at the second part, when we talk about our application in robotic perception, we are going to notice that the data is quite noisy, it's quite incomplete, and it's also limited. So, as well as in some complex personalized systems, such as the body of a person. So we have, these are all situations when uncertainty is a key, a central aspect of the modeling. All right. So, and how are we going to tackle this? How are we going to tackle the uncertainty? So, basically, our tool is going to be probabilistic theory. Probability theory, sorry. So we are going to use probability theory to basically express this uncertainty and manage it in our models and connect it to our data too. So how then are we going to get all of this together and come to a way to predict that number of people getting the bike for a certain temperature in the city? So that's where the learning comes in, right? We have the data and we need to learn something from it. So in this probabilistic approach to machine learning, we are going to understand learning by updating our knowledge from a certain prior knowledge that we have for that particular problem. So if we get the example, we have some prior knowledge for our parameters, for instance, for our parameters of that line, those theta parameters. So we might assume some prior knowledge about that parameters, and given that we observe data, we update that knowledge. And we get what we call a posterior distribution about those parameters. And hopefully, by doing this, we are going to get more certain about the actual information that we need. So we are going to use this framework here, this learning, this update from prior to posterior from now on. So we can understand the prior as a belief, as a first intuition or idea or knowledge about a particular phenomenon that is going to get enriched by data. So basically, this transformation is basically, in probabilistic theory, a condition. We are going to condition our parameters or the thing we want to know about on the data, and then we are going to get a posterior. So that's what we're going to do. So the learning process in our probabilistic approach to machine learning is going to happen through Bayesian learning. And for us to understand what Bayesian learning is, we need to first talk about these two basic rules in probability theory that are called the sum rule and the product rule. So the sum rule is for us to get the marginal probability for, first of all, A and B are two variables, okay, general variables. And so the sum rule the sum rule can be understood as we can get the marginal of a variable, so the probability of a particular variable, by summing over the joint probability over the other variable. So we can sum over B. And then we get the marginal of A. And the product rule is understood as we can get the joint of A and B by multiplying the marginal on A by the condition of B given A. So these are two basic rules in probability theory, and they are our starting points to, hey Eric, so they are our starting points to derive what we call Bayes' rule. So Bayes' rule is this. So the probability of B given A is equal to the probability of A given B multiplied by the probability of B divided by the probability of A. All right. So, but how can we connect this to our previous problem? So we can basically translate these variables into the variables we are dealing with. So theta are the parameters of our line. D is the data that we observed, those 20 points that we observed. And we can condition everything on M. M is our model, is basically what our linear model. So everything is conditioned on that, right? It's the structure of the model that we chose. So what is happening here? What is this learning? What is happening in this relationship, in this equation? So we are basically taking the probability of theta, which is that prior. It's that first assumption that we have regarding our parameters. And we are multiplying it by the probability of the data given theta. I'm not mentioning M because it would be tiresome to always mention M. You know that everything is conditioned on M, right? So let's mention the other variables. So this probability of D given theta is the likelihood. So it's basically what's the probability of my data, of the observed data that I have, given a specific set of parameters. So how is my data explained by those parameters? So that's the likelihood. This divided by the so-called evidence, that's the probability of my data. This is very useful for deciding which model to use for model selection. And all of this is equal to the probability of our theta given our data. So here is the condition. We are conditioning on the data, so we are updating our prior into our posterior. So this is that arrow that we saw before. This is the learning happening. So the data is what is allowing us to learn, right? So this is the Bayes rule. This is how everything is learned, basically, in probabilistic machine learning. That's this thought, or this idea, this philosophy of always updating your prior into a posterior. And then if you see more data, you can always consider that posterior that you have as a new prior and keep on updating that on this new data that you have access to. All right, so this is the learning. So this way we can basically get a probability distribution for our parameters. But we still don't have a prediction or, yeah, some sort of estimation. We still didn't solve our problem, our original problem. And we can basically make predictions by, here we will understand these variables that are of our interest as D star. So that's the data that I want to know about. And so we can derive this distribution by taking this integral of here, this is our posterior. So here we have our distribution, our updated distribution for our parameters. And we multiply this by the probability of our this variable that we want to know about, given the theta. So what is happening here? Here we are filtering out our thetas, right? And all of this is dictated by our posterior. Basically, these are sort of weights that are being used here, and we are filtering this out to theta out, sorry, so our parameters out to derive a probability of our the variable we want to know about. So, and the interesting thing here is that we get a probability. So we don't have a point estimate, but we also know how sure we are about it. We can know more than just estimating a number. We can know how sure we are. Imagine this to be a Gaussian distribution. So we have a variance, and we know if this is too large, we probably cannot rely so much on it. If it's quite a sure prediction, then we might go on with it and decide something relevant. So this slide basically showed what Bayesian learning is. So we are now going to give a step forward, and and we are going to look back to our problem of estimating a function. So what we learned from the previous slide is that we can estimate our line by using that framework, and that would give us some information regarding how certain we can be in different parts of our domain or of our input. Okay, but what if I basically do not want to go on with a linear model? I could try another kind of model. I could try a polynomial of order 2. I could try a polynomial of order 3. I could basically try different models, different parametric models, different ways of explaining this. Yes?
Puzzled by the fact of the band of error, which is narrowing in the middle, and I'm not a statistician, but when doing this kind of approximation, I would say, okay, interpolation is good, extrapolation can be dangerous. Is that something which is exactly the same, would be translated in this band getting wide at the edges? Is that the same in other words?
Yes. So as we get far away from our observations, we get more unsure. So we expect us to have more, to be more secure as we are closer to the data, and less secure when we are getting far away from it. So, but here, what if we don't? Did I answer your question? Okay. So what if I do not want to go on with the line? I can try other kind of parametric models. But what if I actually would not want to specify beforehand this parametric model of the amount of parameters that I would need to model this data or to explain this data? What if I would be able to keep it general and to basically define this problem as just this to start with? It's a regression problem. I want to discover an f of x, a function that explains this x and y's, or these y's that I have, this data that I have. So we are going to look into a way of basically defining a distribution that is over functions. So that's where the Gaussian process comes in. So we want to define, to use Gaussian processes to give us the same kind of framework that we had for our variables, but now transfer it to functions. So how can we actually define a distribution over functions? Actually, we can do that by defining a distribution over the function's values at a finite but arbitrary set of points. So if we imagine, going back to our input domain, we have n points there in our domain, in our input domain. And if we can define this distribution over over our function values in this arbitrary, and doesn't matter which, but defined input points. Okay, we can actually define a distribution over functions. But what is the assumption here? What is the assumption behind GPs or Gaussian processes? Is that this probability of all, and these are my outputs, right? F of x1 until f of xn. So my assumption here is that this joint probability of my outputs is Gaussian. So this is a joint Gaussian. Doesn't matter which input points I will get, doesn't matter the amount, doesn't matter, but all of them they will form a joint Gaussian. This is a very important assumption for GPs. And how can we define the GPs, basically? So we will define them by saying that this function, our outputs, which is actually a function we don't know, we want to understand about, we can call it a latent function because it's sort of hidden under this noise, right? We just observe these things, these y's, but our y's are corrupted by noise, and we want to understand what is happening in this latent function f. All right, so we will understand f as a Gaussian process that is defined by a mean and a kernel function. So this kernel function is going to define a covariance, right? If we have a joint Gaussian, we think of a mean and a covariance. So this is a function that is going to take 2 input points and basically output a scalar. And by using this function, which is a positive definite function, we can compose a covariance. And this covariance is going to be the actual covariance of this joint Gaussian that we need to describe our f. All right, so this is how GPs work. Let's I have some extra formulas here. So this is a little bit of more information about how we define the mean and our kernel. So as I said, this kernel is going to define the covariance of our outputs. So we are always looking for f, right? We want to understand about our output. We want to describe it as a GP, and so we get this covariance of our outputs by basically, and that's I find it very, very interesting, by basically getting this value, this kernel value, on the inputs. So this is a function that is going to give us a measure of how our outputs covary. So basically, this function here, whenever it tells us that 2 input points are similar to each other, this is an indication that the corresponding outputs should also be similar. But this concept of similar is going to change as we change this kernel function. We are not defining right now any kernel function, right? It can be actually many different functions that we can use here. So Um, and this is actually our way of giving to our modeling scenario some sort of we are going to implicit our assumptions through this kernel, through choosing this kernel. So we are basically going to choose how we, by choosing the functional form of our kernel, we are going to choose how we want to our outputs to covary. So let's look at an example. Yes. Yes. This. These are different data points. Yes, different data points. So, yeah, like in our example, all of those points were different data points. So the corresponding axes of those would be the x1 and x5. Cool. So this is one example of a kernel. It's called the squared exponential. And we can see a picture of it. So we basically, this kernel, this function, right, that takes two input values and outputs a scalar, a measure of similarity. It takes two hyperparameters. Here we have the what we call intensity and L, the length scale, these two. And usually kernel functions have hyperparameters. We can define them in different ways. We can define them manually, just setting a number. We can also submit this through an optimization procedure and maximize some function, usually the marginal likelihood of our model, in order to find the optimal values of these hyperparameters to explain our data. We can also use Bayesian methods to set them. There are different ways, but what I wanted to show with this example is that this is a very common kernel function. And what happens with this function is that it basically the covariance between your outputs, they smoothly decay with the distance. So as you get more distant, it smoothly decays. So that's the implicit assumption in this kernel. Cool. So let's now go back to our example. And here, let's look into some... I need to speed up. So let's look into an example. So this is a GP prior. So what I defined here was, here in this slide, I basically defined a mean, and I'm using this kernel, this squared exponential kernel, to define a prior, a GP prior, a Gaussian process, a prior to our function f. And what is happening here is that I am basically sampling from this prior. As we sample from a probability distribution, here I'm sampling functions that can be the functions that we are looking for. Here I am not observing any data, I am just sampling from this GP that I just defined. So I sample by discretizing my input domain and then calculating the GP and then calculating this joint Gaussian and then simply sampling from this large joint Gaussian. And then when I plot it, it looks very smooth because I have quite many points here, 400 points. Cool. So this is updated as soon as I see some data, right? And then we can get the posterior, which will be, again, a Gaussian process, and will be described by this formula. This big K, these are just matrices defined by our kernel. But you remember our kernel, so that function is going to define these matrices. And with that, we can calculate our posterior. I am not going into the details of this. I will show you the posterior. And here we have our same data points, and this red line is our mean of our GP posterior. All these other colorful lines are samples from the posterior, and this space, this shaded area, is showing how certain I am about this estimation in different areas of my input domain. So that's very interesting, because as soon as we are close to the data, we are more certain. As soon as we are far away, we get uncertain. And we also see from the samples that they tend to be larger in areas where we have a larger uncertainty. So this is an illustrative example of a GP in 1D, yes, in the domain, in 1D domain. Cool. I think it's time to start talking about how we can use exactly the same concept, but in a different problem. So now we will see how we can use GPs, Gaussian processes, to create 3D probabilistic shape estimates of objects. And this can be done to aid robots to do various tasks. So let's look into it. So here we have a Kinect camera, a typical sensor used to show objects, the robot workspace to robots. And here basically this Kinect is capturing this real scene, and this is the representation that it captures. Yes. We also have different kind of sensors that we can use. We have Kinect, we have tactile sensors, for instance. There are lasers, there are different ways of collecting data from the environment. So basically we have the sensors, and what we will do here is we will get some point clouds from these sensors. We will look into two sensors. We are going to use a Kinect, and we are going to use also tactile measurements from the interactions of the robot hand with certain objects. So we are going to have these two sources of data, and they are basically point clouds, which means they are 3D points in the space, so X, Y, Z, and we will have quite many of them. And from this point cloud, what we want is to estimate a shape. We want to estimate shape of object. And why do we want to do that? It turns out that understanding shape of objects is something very useful for different tasks of robots. For instance, to estimate the position and the orientation of objects, as well as to aid the robot to plan how to grasp different objects. And why uncertainty as well? Why would uncertainty play any kind of role here? For instance, in grasp planning, whenever a robot has an estimate of how an object looks like, what it wants is to pick an orientation that is going to increase the chances of success in that grasp, right? So we want to be as sure as possible, as smart as we can be, given the data that we have. So uncertainty is going to play a key role here. We are going to see it later on. So what are the challenges? Let's imagine that this line here is a surface of an object, okay? So let's imagine this is a surface, and these points are, points collected from the surface of this object. So these are measurements from our sensors, for instance. Here, first challenge is noise. We see that the points are not correctly positioned on the surface, and this is noise, basically. Measurement noise. One challenge. The other challenge is mismatching data between these two different sensors. Sometimes we do calibrate the sensors and we do translate them into the same frame, but it does happen that sometimes there is a mismatch between these measurements. So this is another kind of challenge. And it also happens that we have missing data. Surface is a continuous area, but we don't really have data for all of it. So it happens to be incomplete often. So this is another challenge. And given all of this, we decide to go for probabilistic representations, and particularly, we will use GPs. So what is our approach here? Our approach is to reconstruct the surface of objects through GP regression in the 3D domain. So again, we will have a regression problem, right? Defined this way. We will assume that our outputs are corrupted by noise. We will assume this noise to be Gaussian, to be zero mean Gaussians. And that's the difference from our previous problem. Our inputs are in the 3D domain, right? So we have inputs in the 3D domain, and F is going to map these points into a scalar. Cool. So we are going to define our prior for F, which will be a GP with a mean with a particular kernel. And what we want is to derive the posterior to start to basically estimate the surface from this posterior. That's our goal. All right. So I didn't mention yet, but there is a particular challenge when it comes to GPs, which is that as your data grows, your computational demand grows too. So basically, basically we have a complexity of n to the power of 3 due to the inversion of our kernel matrix, which gets bigger as our number of observations increase. So this is a disadvantage. So what we will do is we will use a variant of GPs. It's a sparse GP. So there are different ways of defining sparse GPs. We are going to pick a specific one that uses a variational formulation. Okay? So I am not going through all the details of the variational formulation, but I'm going to pinpoint the essential aspects of it. So basically, the first essential aspect is we are going to reduce our complexity from O n to the power of 3 to the complexity of n multiplied by nu. And what is nu? This is basically the number. Oh, n is our number of observations, right? And then nu is the number of inducing variables. Basically, this is going to be much smaller than our n, and these are going to be new variables that we are going to add to our modeling. Okay, so what are these inducing variables? We have some inputs, x, and we also have the corresponding outputs, f. So we have both inputs and outputs, both inducing inputs and inducing outputs that we are going to introduce. Okay? It turns out that these inducing inputs will need to be optimized. They are going to be part of our optimization procedure that I will explain later on. So basically, what is this variational formulation? So we are going to define a different posterior. Here in this posterior, we have we are not inverting that huge matrix. Now our matrix is as big as XU, so XU by XU. So we are avoiding that big inversion. Great. This is an approximate posterior. And what happens here is that this is a distribution that is going to, through an optimization procedure, we are going to approximate this to the true posterior. So this is equivalent to minimizing a distance between two distributions. So we are going to use this minimization is basically we want to minimize the KL divergence between from the exact posterior to the variational counterpart, this one. Okay, and this is also the same thing as maximizing a lower bound to the exact log marginal likelihood. That's our objective function, right? That one that I mentioned in the beginning. It's a way for us to it's our direction when we want to optimize any parameters. We want to look at our marginal likelihood, and we want to use it as our objective function. Okay, so we basically this variation approximation creates this posterior, and we are going to use this optimization to define a set of parameters. Okay, so this set of parameters is these inducing inputs, our kernel hyperparameters. You remember that I mentioned that there are some hyperparameters. They are going to be optimized too, as well as our noise variance. That noise added corrupting our outputs. So we are going to define all of these to an optimization. Great. So our approach, another important part of our approach, we are still not sure how to get a surface, right? So we are going to get a posterior distribution. And where is the surface? Basically, we are going to understand this surface as the level set of our underlying GP. Okay, so let's imagine a function like a bell. If we have like that normal distribution that we saw over here in some slide before, if we have this bell, and let's imagine that we cut it in a particular value, what we will get is a closed circle, right? Or ellipse or something closed. And in that is we can call it as the level set of that function. For the level set is the number, and by using that level set, you can get basically a surface if your original distribution is in the 3D domain. So, and that's what we have, right? We have a function in the 3D domain mapping points to a scalar. So, yeah, so we imagine, us having many points in this 3D domain, and imagine us getting the level set. In this case, it will be the level set 0. I will explain soon. We will get this level set to induce the surface of our objects. So, okay, but how can we guarantee that this is going to be closed and this is going to be like that? So, we are going to induce this by basically, look, here it's an example of a point cloud. So the black points are the surface points. And we are going to give all of these surface points, these are our observations, we're going to give them the value 0. And we're going to add we're going to match them to the value 0, right? And we are going to add some additional points, both outside as inside the object. And we are going to give a positive value to everything that is outside and a negative value to everything that is inside. In this way, we are creating this topological condition that we need to extract the level set of our GPs. So that's our approach. We are getting our observation, matching it to 0, and then we are going to add some points outside and match it particularly to 1, and a point inside in the centroid to -1. This whole approach is called Gaussian process implicit surface because we are creating this implicit surface through GPs. Cool. So, exactly. So these are the points that, these are the values that I just described. All right. So this work is basically an extension from a previous work that's investigating shape learning through GPs. We are going to use this data collected by this work, and basically the ways we extend this work are in 3 ways. We are going to use sparse GPs, so we are not going to need to sample data to reduce our set of observations. We are basically going to use the original set because we are using a sparse approach. So this is the first. The other thing that we do is this optimization of hyperparameters and of the others, of the variance noise, as well as the inducing inputs too. So we are optimizing these parameters, things that basically here were manually set. And we are also adding additional investigation on synthetic data. So we are also seeing both synthetic as real sensory data. Cool. So, yes. Thank
Sure.
you.
So you said that you added points in the bottle and without outside
Yes.
the bottle. How do you decide on where to add those points?
Good question. So basically the one inside is in the centroid of our points. And the ones outside, we are getting we are getting the distance from the centroid to the farthest point, adding 10%, and sampling from this sphere that has this radius. So to guarantee that these points are outside the object.
So you just add 1 point inside. And
Yes,
yeah.
it's enough. It could
Yeah.
be more, but it's enough to provide the topological information that we need. Cool. So this is an outline of the work. So this figure shows what we have done. So basically, we have raw data. The black ones are from the Kinect. The pink ones are from the tactile sensors. We transform this into an estimate, into a surface estimate. So how does it work? We have some data pre-processing, we have some centering, some normalizations, adding these points as topological information. We define a prior distribution of our GPs, and then we get into an optimization procedure. So basically, here we will have our GP defined, and then we will have a bunch of parameters that I already mentioned that we need to optimize. And for that, we will use an optimization procedure called limited memory BFGS. It's a quasi-Newton method that uses some bounding constraints too. We have 2 bounding constraints that we use here. We are going to use this procedure to determine our parameters. After this, just on the bounding constraints, these are just some constraints to guarantee positive semi-definiteness in our kernel. I can talk more about it later if you want. So these are, we have this optimization going on. Then after this optimization, we basically define our posterior. So we have finally the function that we needed to describe our surface. Then we take the level set, right? Level set 0. And this happens through a procedure called Marching Cubes algorithm that extracts this level set and gives me back a triangular mesh defining the surface. And then we have it, and this is it. The colors talk about the uncertainty that we have been talking about. Cool. And then when we have our surface, we go through an object clustering procedure too. This is just some additional knowledge about our objects that we extract from this representation. We can basically cluster them based on some basic shape characteristics that we can see from this representation. Okay, so I will show you quickly some. Yes.
The last step of object clustering, is that just to smoothen out the surface, to clean it up, or I didn't understand what those last 3 steps were?
Okay, so the goal, you mean the goal of the object clustering? Goal of the object clustering is for the robot to know which object looks like which object. So how could I separate them based on this? How could I distinguish them based on this surface representation? You will see that we have some cylinders, some boxes, for instance, and then they are basically clustered in different clusters.
Okay, so that means that if you have like different objects on a table, for example,
yes,
the object clustering just says like, oh, all of these points, all of this belong to the cube, all of these belong to the cylinder. Is that what it does?
It clusters the surface, the object, the complete object.
Yeah.
So this is the motivation behind it, is that objects that look alike basically will require the same kind of grasping.
Okay.
So, for instance, for cylinders, you probably could approach them in the same way. So that's the motivation behind the object cluster. Yes.
So relating to this, you have already clustered. You already have point clouds which only relate to one object. So you don't have multiple point clouds in the same set or same sample. Is that true?
That is true.
Yeah.
Yes.
Thanks.
So it's optimizing for every single object. A possible extension of this work would be to basically get things together. So be able to infer things from an object based on objects that are similar to it, and understand additional things about this surface based on other already modeled surfaces. But so far, everything is separated. The optimization is made for every single object. Yeah. Cool. So our data set. Throw your questions, people, because yes, because yeah, just throw whenever you have a question. Cool. So this is our data set. This is our synthetic data set. It's from it's a data set collected by some Princeton group, and it's available in the internet, and it's basically triangular meshes of different objects. So we have some apples, some pots, bottles, and ducks. And this is the collection of the real sensory data set. So basically there is a Kinect, there is the robot hand with these 3 fingers with tactile pads on it, and yeah, that's our 2 sources of measurements. So I will show you the objects, how they look like. So we have boxes, we have some cylinders, as well as some spray bottles. Great. So this is what you will see in the results. So this is, for instance, an object, a point cloud from the synthetic dataset. From here we have our estimated surface. What do these colors mean? So the blue means low variation in our posterior. So here it's the standard deviation of this predicted distribution from our posterior GP. So the blue means I'm sure about it, and red means I am not so sure about it. So here, this is what it's called a probabilistic occupancy map. It's basically a plan cutting the object and saying what is the probability that the object is occupying that particular point. Okay? So these are ways of evaluating our results. I'm going to show you some of the results that we have. I will need to be very quick, but basically what I want to share with you is that these experiments were done in two parts. So the first part was an explorative part, an explorative phase. We didn't want which kernel function to choose, for instance. So we basically analyzed some of them. We wanted to know how close it gets to the full GP prediction. We are doing a sparse GP prediction, right? But we wanted to get as close as possible to our full GP, so we also did some analysis on this. And then we predicted the surface for all these objects that I showed. We calculate some distances to the ground truth too, as a way to compare things. It should be close to the ground truth. And finally, we did some object clustering to see how much of valuable information do we get in these representations, in these surfaces. Can we cluster our objects based on them? So this was the study. So you will see here some pictures. These are the 3 different kernels that we analyzed. The first one we already talked about. We have the pattern kernel, and we have also the template kernel. So here are some results for these different kernels. So here is our synthetic dataset, 4 objects, 1 from each class. Here we have the predictions for the square exponential, the pattern, the template, as well as the corresponding probabilistic occupancy maps. So here you see, square exponential, as expected, tends to smoothen out our surfaces. Pattern performs better, but the template keeps the shape characteristics much better than the other 2. So that's the one that we stick to, and we continue our experiments with the template. These are some distances that we measured. This is a comparison between full and sparse GPs. Basically, the takeaway here is, if we look at our sparse, it's always the second. The first one is the full prediction, and the sparse one is the second. We can see that the sparse tend to be more insecure. This was expected because we are approximating things. But if we look at the mean, at the estimate, they are very, very similar, very close. So we make some comparisons in terms of distances too, and you can see that they are very similar. I'm sorry that I am passing so fast. We can talk after. Yes. So basically, this is the reconstruction of the surface for the other objects of the synthetic data set. So you can see all of them. From here on, we call it the second phase of our experiments, the exploitative phase. We already decided what is the kernel that we want to use. We have already seen that our predictions look very alike to our full GP predictions. The distances, they make sense. So we go on with this kernel choice, and with our sparse GP too, and we basically reconstruct further surfaces. So this is for the objects of the real sensory data set. So you can see that there is much more noise here, much more noise. So we can see that the surfaces, this is a box, this is a cylinder, this is a spray bottle. They are much more undefined, or the shape resembles less the original object in comparison to the synthetic, right? This was expected because our data has noise and due to all those challenges in the beginning. Yes?
Yeah, I was going to ask something. You said earlier that the black points are the connect, right?
Yes, exactly.
So can you just briefly explain how come that the Kinect is creating like bumps on a smooth surface? So for example, in the second shape, the cylinder, the one on the left, if you look at the black side of the...
Here?
Yeah, at the top,
Yes.
there is like a bump. Do you know why the Kinect create, or why is that recognized as a point by the Kinect?
Why the bump exists?
I mean, was it in the original surface? Was it?
It was no, it was not in the original surface.
Yeah, so why does it appear there? That's basically my question.
Okay, so, well, the data collection was from the previous study. I was not part of the data collection, but I can think that...
So maybe I can fill you in, because I can understand that maybe the actual touching might be much more error prone. I'm a bit surprised that the Kinect is also, well, apparently very unprecise.
Yeah.
Yeah, that
So-
was basically why I was wondering why that might be.
I will go with your answer. So I am not sure why there was this bump here particularly, but basically for every single touch, a new collection of point clouds was taken from the Kinect. So for every single touch, because every touch involved a little bit of movement, right?
Okay, yeah, that might
So,
explain it.
but anyway, I'm not sure why there is this bump here.
Thanks.
So we have these surfaces reconstructed, and let's look into some. This is a comparison that we have done with the previous work. Basically, the previous work used the full GPs, right? We use the sparse GPs. We have very similar distances, but in the mean square distance, we basically use two distances, the mean square and another kind of distance called Hausdorff. In the mean square distance, we noticed that the arrows, or sorry, that the previous work performed better. Yeah, a little bit better when we compare. So, but if we recap here, we are basically using a sparse approach, right? And we are doing an approximation. So we are glad with this distance graph, even though it is not always on top of in the comparison. This is my last slide, and this is the last evaluation we did, which is how can we cluster our objects based on this representation. And for this, we use the spectral clustering. And basically, we use spectral clustering on similarity that we calculated on features of these surfaces, and we use the features that we use are called principal curvatures that collect curvatures measurements in different points in our surface. So this describes our surface. We basically have a similarity measure comparing different objects, and from there we do spectral clustering, and here you see the results. Here in the first row, synthetic data set, here under real sensory data set. So you can see here in the beginning, when we cluster our objects, we have 2 objects that are misclassified out of the 12. And here in the real sensory data set, we have all of our objects correctly classified in spray, in boxes, and in cylinders. So this is just an additional clustering we did, setting just 3 clusters instead of 4. This is interesting because it shows that basically here this cluster captures everything that looks a bit cylindric, bottles, everything that looks like round apples, and everything that looks too weird, like ducks and pots with more complex curvatures, into one single cluster. So these results show that we are able to use our probabilistic representations, our GPs, to both have an estimate of how our surfaces look like, to know in which areas of our surface we can trust more, which areas we should not trust, which areas we should probably explore further through tactile exploration, for instance. And these probabilistic representations also allowed us to distinguish our objects in these basic, in these clusters. So I hope you had a feeling of what probabilistic machine learning is and how we can use it in robotic applications. Thank you very much. Cool. Cool. Yes, do you have further questions? Yeah.
So I wanted to ask you, what is the running time for like a single object?
Good question. So, what is the running time? So for us, so all the objects, okay, all the sensory, from all the objects from the real sensory data set as well as the synthetic. So the one with the biggest point cloud, which had 14,000 points, it took 5 seconds to calculate the posterior, derive the posterior, and derive the triangular mesh from it. The one with the smallest data set took 4 seconds and something. So 4 or 5 seconds. However, optimization of parameters was a very very slow procedure. So that was when it took the most time. For the biggest data set, it could take until 30 minutes to optimize all of the parameters. We were using quite many inducing inputs, 350, so this influences a lot on the optimization time. However, a positive thing from it is that usually you don't need to optimize things in online, in real tasks. These parameters could be already optimized beforehand. So yeah, so this is good. Yeah.
You said something now that I didn't hear, that you were using something that influenced the optimization a lot.
Yes.
What was that? Do you remember? You were using hardware, or?
It was the inducing inputs. So the number of inducing inputs, basically those additional variables that we added to the modeling to make the GP sparse and to use this variational formulation to approximate the posterior. So there were many, we used many inducing inputs there, and so we had this just adds parameters to be optimized. So.
But that was to make it. Why did you do that again? Maybe I
so the more inducing inputs you use there, the closer you can get to your true posterior. So we had a trade-off there to choose. So we did some experiments with different numbers, and we found a reasonable number there in 350, and so we went with it.
So what I wanted to ask was this.
Yes, sure.
So what did you optimize over when you were doing hyperparameter optimization? Which were the different categories and numbers? Like the shape of the kernel is something that you did hyper optimization over. Is that true?
We did optimization. So given a kernel, we optimize on the values of the hyperparameters. For instance, in the thin plate kernel, we have one hyperparameter that is basically the it's a hyperparameter called R usually in the papers, and this we basically set an initialization value, some constraints so that it doesn't go wild, and our covariance, to keep our covariance positive semi-definite. So there we optimize this hyperparameter basically. But this is given the choice of the kernel.
Okay, so and that was the only thing you hyper-optimized.
So that was one thing we optimized.
Yeah.
We also optimized the noise, the variance noise. This was also completely defined in the optimization. And the inducing inputs.
Right.
So these are all the parameters we optimized. So for the square root of exponential, for instance, it is that the intensity and the length scale, they are optimized to the hyperparameters. And the mattern also. So we optimize all of them. Yeah.
Thanks.
Cool.
Yes. What did you do to ensure that you had the right model? I mean, suppose that the variance or the uncertainty was 100 times as much as it should be. How do you know that the model was correctly chosen? And could you how do you see that it was not correct afterwards?
So how we can choose the model given the uncertainty in the data?
Yeah. How do you know that the model fits the data, so that you maybe if the kernels were wrongly chosen, you could have you think you're much more certain that you are. You could be thinking that you're 100 times more certain that you really are. How could you see? How can you observe that or see that afterwards? Or how can you ensure that you're not you make a correct model choice?
So by model choice you mean kernel choice?
Yeah.
Yeah, because the idea of picking such a flexible way of approaching this problem, GPs, is basically that we don't want to specify so many assumptions beforehand. We want it to adapt to the data that we provide. So this is a big motivation of using the GPs. Regarding the kernels, we went through these three kernels, and we wanted to compare them to basically go for some sort of direction in what fits better and what adapts better. What are the assumptions that fit better to this particular problem? However, we also noticed that there could be ways actually to improve our approach when it comes to kernels. We could, instead of defining such a broad prior, we basically defined a very broad prior with mean 0 and the particular kernel. We could also have defined some geometric priors. Basically beforehand we could say, for apples, for instance, this is a sphere. We could add some priors that already say beforehand that those objects look like an ellipsoid or like a sphere. There are studies that use geometric priors. So I believe this would be something very enriching for this particular problem, because we would just convey more information already beforehand. And regarding the uncertainty and the noise and everything, we basically have a representation that shows whenever it's very noisy and data from different sensors mismatch and things are very confusing, it gets unsure. So we can see it by seeing the surfaces, by seeing the triangular meshes and the colors. Yeah. Did I answer your question? What was your question?
The question was really, how can you know that the uncertainty or the variance you get is the correct variance? Is it somehow, in some sense, correct? I don't know if it's a sensible question, but suppose that one model would give 100 more certainty than the other.
Yes.
How do you know that one model is correct and the other not correct? How do you know that you can trust the model you have? What do you do to trust that?
Yeah. So here, basically here, we had the chance to have access to the ground truth and to always have a reference point that we could use to compare things. So that we basically use that as some sort of reference to say, okay, this looks unsure, but let's see how the mean compares to the ground truth. But I agree with you that it's an open question. Basically, sensor noise, estimating the sensor noise from the beginning could be also something, could be also, could help to set some initial values for the Gaussian noise, for instance. But we didn't go there in this study.
Relating to that question, you said that priors could help you in this project. Could it help you in terms of like convergence speed or actually getting a better result, or both?
Getting a better result.
Yep.
Yeah.
You ended up with a complexity that was square to the size of the input variables, and that took you 5 minutes of solution time.
5 seconds.
5 seconds, okay.
Yeah.
For, I don't remember how many points.
14,000.
14,000. So the guys before you that had a cubic relation, how much time did that take? Was it, is it just the square or the amount of points cubed? That must be a very long time for those guys.
Yes, but those guys, they sampled the, so the study before got the point cloud and basically sampled from it, because it's computationally not possible to get 14,000 points into a vanilla GP, and I tried and I got memory errors. So so basically what they did is they sampled. So from starting when they cut off some points, made it much smaller, and went through the full GP solution.
And so when you compared, you compared to their sampling. You said that you had some comparison of exactness, and so you compared to their sampling. Is okay? Yeah, I do see. Thank you.
Okay, cool.
The kernel function that you elected, those the best one, it was not the same one that you showed in the beginning, right?
The best one was not the same one that I showed in the beginning. Okay. Exactly. So the one that I showed in the beginning was the squared exponential. That's the one that outputs a covariance that very smoothly decays with the distance. So
you can't show like a similar shape for the best one, the TP.
Yes, the thin plate was the one that performed the best.
And it has no like equivalent shape. It does
not
decay
no,
to
no. I don't have no. It doesn't have an equivalent shape.
Okay.
True. True. Are there more questions? Then thank you. Thanks a lot. Cool. Tack, Sara.